Awesome. Okay, so we've just started the recording. We are live with the recording. I've answered a quick question from Scout, and I'm going to go ahead and just put that equation on here for all of us to see. She had a question about gravitational force versus gravitational potential energy. Turn that off. Okay, so these two equations are very similar to each other. Gravitational force is the gravitational constant mass 1 times mass 2 over the distance between the centers squared. So if this were the Earth and this were the Moon, then R would be the distance between their centers. So from here to here, that's going to be the R distance. So you've got to take into account the radius of the Earth plus the distance between the two objects plus the radius of the Moon. And that gives us the force. So we can see that if the masses are staying the same, Ethan, the gravitational constant is a constant for our universe. It is 6.67 times 10 to the negative 11, and it has a unit of a Newton meters squared per kilogram squared. This unit looks pretty complicated. You don't have to have that memorized. That is on the formula chart, and in fact, you'll probably never even need to write it. You don't have to memorize the value either. It is on the formula chart on the back where the constants are. So this is a number that never changes. And then we have the mass of the first object times the mass of the second object. In a scenario where, let's say, I could magically move the Moon to twice the distance. So now I'm going to move the Moon way over here. And so that R value, let's say that R value has doubled. The total R value has doubled. Well, I didn't change big G. I didn't change the mass of the Earth. I didn't change the mass of the Moon. The only thing I changed was this R value. So in response to that change in R value, the force between the two objects are going to change. So I'm going to strip away everything that did not change, and we're going to see that the gravitational force is not equal to, but it is proportional to 1 over R squared. The reason I write the proportionality symbol is because, again, it is not equal to, it is proportional to. But we see that this is an inverse square relationship. In an inverse square relationship, the force is dramatically going to decrease as this radius increases. Let's say, for example, the distance was 1. Well, what does the force equal? The force equals 1. But now if I double the distance, I have to square that double distance. So now the force is 1/4 of what it is. So where the R value is doubling, the F value is actually being reduced by a factor of 4. And so this is an inverse square relationship. It tapers off very quickly. So that is our force equation. Now, if we go back to our gravitational potential energy, oh, by the way, force is still measured in newtons, and energy, U sub G, is going to be joules. They are not the same thing. So our equation for gravitational potential energy is big G, M1, M2 over R, and then there is this negative sign out front. Okay? So the only difference we see between the two equations, the only difference we see between the two equations is this negative sign and the fact there is a squared value there and there's not a squared value there. So one might think that the relationship between potential energy and potential energy and distance is similar to that of force and distance. It just doesn't decrease as quickly. But the negative sign makes all the difference in the world. Because this is a negative, it's really saying that this potential energy does the opposite thing that the force does. So as the distance between the centers increases with force, force decreases, right? But over here, if I have an increase in R, I actually have an increase in gravitational potential. Now, mathematically, what we would see is that I would have, let's say I have a -1/1, and that's going to equal a -1 joule. But if I double this R value, now I'm going to get -1/2. Of course, that is equal to -1/2. And I would ask you, which of these numbers is larger? Larger on a number line, -1 or -1/2? -1/2 is actually larger than -1. So as the distance between the centers increases, we also get an increase in gravitational potential energy. And so if we were to take the negative sign away, it would appear like it gets smaller, but because that negative sign is there, it actually gets larger because this is a scalar value. All right, Nick says, you said that you use the force equation when on the surface of the planet and the potential energy equation when you were in space. Nick, you have that almost correct. We are going to use, there's two equations for gravitational potential energy. The one we used at the beginning of the year was mgh, and the one I just showed you is -g m1 m2 over r. These are both on the formula chart. This is the one you want to use when on the surface of a planet. This is the one you want to use when you are in space. The reason you can use this one when you're on the surface of the planet is because the gravitational field is approximately 9.8 meters per second squared, and the field is uniform. At the surface of the planet, the field doesn't vary enough for there to be a dramatic difference in the gravitational potential energy. But once I am measuring the gravitational potential energy between, let's say, the Earth and the Moon again, that's when I want to use this equation here, the second one. The same holds true with your force equations. So we know the force equation that's equivalent to this one is F of G equals big G m1 m2 over r squared. Definitely want to use this equation when I am in space or I am looking at an orbiting body. But if I'm on the surface of a planet, then I can just use F of G equals mg. And the reason that I can use this simplified version when I'm on the surface of the planet is because this G value is not changing, again, because we're in a uniform field. So if I compare these two equations right here, I can see that this little G value really is representing big G, mass of the planet, divided by the radius of the planet squared. Say hi, Emmy.
Hi.
Hi. Emmy's here, and she is saying hi. Let's go back over to our... Oh, there's Parker. Say hi, Parker. All my students can see you. Did you just snort? She snorted, and everybody heard you. Okay, let's go back over to my little drawing. So this little g for the gravitational field strength of any planet, of any planet is going to be equal to big G, mass of the planet divided by the radius of the planet squared. So whenever you compare these two equations, you can see that this right here is really just the G value for any planet. And then if I multiply that by the second mass that is experiencing that gravitational field, well, then that's when I can determine the force between those two objects. And you can see because it took both masses to determine the force between the two objects, then the force between the two objects has to be equal.
Mommy, can I draw something?
And don't go play, okay? All right, next question. That was a great question, Scout, to start off the evening. It allowed me to kind of go over that gravitational potential energy equation that we did last class, and I know that that was kind of quick for a lot of you. So if you still have questions about that, please do ask. But let's go ahead and move on to another question. I haven't seen any more updates on the chat, so hopefully everything is still connected and working. And I'm looking for some more questions from you guys. It can be about the test review, it can be about the practice test, anything we did in class, like Scout just asked. Somebody say hi real quick so I know that the chat's still working.
Guys, go sit in the dining room again.
Awesome. Okay, so John said hi. Thank you, Caitlin. Can you do number 20? Reese, is that on the test review or the practice test? I'm assuming practice test. Good. Okay, let me pull up the practice test. Number 20. Okay. I think... See if I can pull this over. Still see that. Okay, a hypothetical planet orbits a star with the mass one half the mass of our sun. The planet's orbital radius is the same as the Earth's. Approximately how many Earth years does it take for the planet to complete one orbit? Okay, so we need to first write down what they've given us and what they're asking us to find, because then I need to be able to find an equation that's going to relate those variables together. So, the star, hypothetical planet orbits a star with mass one half the mass of our sun. So, sun mass of the new planet, of the new sun. So let's just say new sun. Say mass of the new sun is equal to one half the mass of our sun. So NS represents new sun, S represents our sun. Okay. The planet's orbital radius is the same as the Earth's. Good. So we're going to say the radius of the new planet equals the radius of the Earth.
You want a hamburger?
Approximately how many Earth years does it take for the planet to complete one orbit? So they want the time that it takes to complete one orbit of the new planet. And they want it in Earth years. So the time that it takes for Earth to complete one orbit in Earth years is just 1 year. Okay? This is all information that we need to know. So now we need a relationship or an equation that relates all of these variables together. I apologize for the noise. It's usually not like this. Okay, an equation that relates all of these variables together. Mass, radius, and period. Zach says he can't learn with the noise. Zach, are you being serious? Okay, I guess I need to move. Oh, he's kidding. Okay. I was worried. Sorry. All right, let me go back over here. Okay, we need an equation that relates mass of the central body, radius of the orbiting body, and period. So, first of all, you probably have no idea where to begin, but this is centripetal motion. An orbiting body is centripetal motion. So I know that the centripetal force equation is mv squared over r. Anytime you don't know where to start, you just start writing down the equations that you know pertain or could pertain to this situation. And then you find your strategy from there. So centripetal force is mv squared over r. I know that the centripetal force in this case is a gravitational force. And the gravitational force for an orbiting body, we're not on the surface of a planet, is going to be big G m1 m2 over r squared. Okay, so because the gravitational force is the centripetal force, I'm going to set these two equations equal to each other. And we get G m1 m2 over r equals, r squared, equals mv squared over r. Now I'm going to put in the subscripts for my planets that match what I need over here. So we have the mass of the sun, the mass of the earth, and then we have, or we'll say the new planet, right? We're trying to get the new planet. So this is the mass of the new planet. This is the mass of the new sun. And then this is going to be the radius of the earth, which is equal to the radius of the new planet. So all that looks good. I'm going to rearrange and cancel some things out. This squared is canceled out by this r because they're both on the bottom and opposite sides of the equation. They cancel each other out. Mass of the planets on each side cancels out. So now I'm left with G. And what I'm going to do here is, instead of saying mass of the new sun, I'm just going to say half of the mass of our sun. So we have times 1/2 the mass of our sun, because I'm putting it in terms of our sun. And then we have the radius of the planet equal to the v squared. All right, see how these two are equal? The mass of the new sun is equal to half the mass of the sun. So if I put this in terms of our system, because we want it in terms of Earth years, I want the mass of our sun in there. But that is 1/2 that mass is equivalent to the new sun. Okay, so the only thing that I don't have in my equation yet is period. Let me move this over real quick. Okay, Ethan says, how are you allowed to equal the two equations to each other? Sorry, I'm confused. No problem, Ethan. This is a very common thing that we do in the process of deriving our own equation. So in this case, we know that centripetal force is just a net force. And in the case of a sun with an orbiting planet, the net force acting on that body is a gravitational force. So really, this centripetal force is just a name we call the net force that causes something to turn in a circle. But what is the type of force that's really making this planet move in a circle? It is the gravitational force. So I could say that this really is F of G equals mv squared over r. If f of g equals mv squared over r and f of g equals gmm over r squared, then I can set those two equations equal to each other. So now I'm at the point where I've got these two variables, mass of the new sun and the radius of the planet in there, but I don't have period. So how can I introduce period into this equation? Yay! Awesome. Glad that helped, Ethan. So the reason why I need to put period in here is because that's what they want the answer in, right? They want to know how long it's going to take to orbit in Earth years. How long it takes to orbit, that is a period. So you can remember that the tangential velocity is equal to the circumference, which is 2 pi r, divided by the time it takes to go around one complete revolution. That is the period. So I'm going to take this and I'm going to substitute that in for the velocity. So now I'm going to have G, mass of our sun, over 2rp. Notice I brought the 1/2 down. And I'm going to equal that to all of this squared. So V is squared. So now I've got to square every single one of these terms. So that's going to become 4 pi squared r squared over t squared. What is this r? It is still the radius of that planet from the sun. This is the mass of this Earth, sun. There we go. All right, so now we're going to simplify. I'm going to combine my r's. So I'm going to take this r and multiply both sides by this r. And that gives me a value of r cubed on the right-hand side. And then I see I have gm over, gm times t squared equals, I'm going to move this 2 over to the other side too, 8 pi squared rp cubed. Okay, so I have everything in the numerator. I have everything on top. So I can see gm, mass of the sun, t squared is equal to 8 pi squared r cubed. Now, the mass of the sun, let's see, big G is not changing. The pi squared is not changing. The radius is not changing. The only thing that's changing is the mass. So I have to see what the relationship is to mass and period. And if we go back over here, you can see that I wrote on the key t squared is proportional to 1 over m. And the way that I got that is by looking at this final equation here. Well, everything is staying the same except for mass and period. But they're on the same side of the equation right now, so it makes it a little difficult to see the relationship between them. So if I move mass to the other side, I can see that t squared is proportional to 1 over m. We want to solve for t. So I'm going to take the square root of both sides. So t is going to be proportional to 1 over the square root of m. Now that I have my proportionality set up, I go back and ask myself, what's the difference between their mass and the sun's mass? So the sun, their sun's mass is half our sun's mass. So we've got to plug in a 1/2 right there. So I get 1 over the square root of 1/2. And what does that become? Oops. Don't want to do that. It becomes the square root of 2. So the final answer is the square root of 2. Let me delete some of this real quick. Go back, go back. There we go. So in the end, we got t is proportional to 1 over the square root of 1 over 2. Whenever I flip this, that comes out to be equal to the square root of 2. Now this is the factor by which the period is going to change. So if the period of the Earth is 1, then the period of the new planet is equal to the square root of 2 times 1. So that comes out to be the square root of 2, which is about 1.41 years. So because its sun has less mass, there is less gravitational force between the two. So it's going to take longer for that same planet at the same radius to orbit its sun. So about 1.41 years is the new planet's in Earth years is the new planet's period. So we really could have eliminated choices A and B because a smaller sun would not yield a greater, or sorry, it would not yield a less period or a lower period, right? A period of a lower value. So their period wouldn't be lower than ours, which means it was faster than our orbit. So it had to be C or D, but you had to know the relationship. And so what I did here, where you see the t squared over r cubed equals 4 pi squared over gm, this is a common derivation that we use when we plug in the velocity equation, 2 pi r over t. This is a common derivation. So I already knew what that derivation was, but I just showed you in the video how we got to this point. Once you get to this point, you can eliminate everything that is not changing. The 4 pi squared isn't changing, the r cubed isn't changing, the g isn't changing, so really t squared is just proportional to m. Okay, so that one takes a little bit of work if you don't readily know that derivation. So anytime there's a constant in an equation, do we cancel it out? Braxton, if you're trying to set up a proportionality, let's say they don't give you actual numbers. They just say that the radius was doubled, or the distance between the two the planet and the sun was halved, or the mass of the new planet was quadrupled. When they give you situations like that, you can start with the equation, but then you can ignore those constants, because the constants are going to be the same in both scenarios. Let's say when the mass was, let's say, 1,000 kilograms, and then if the mass is doubled to 2,000 kilograms, well, that g, that universal gravitational constant, is the same in both scenarios. So it's not going to affect your overall multiplying factor. All right. Abby is asking for 2B on the review. So let's look at the test review. 2B. Yeah, they both say A, but I'm assuming you're talking about the second one. Okay, so it says, for each part, rank the 4 cases based on which pair of objects exert the greatest gravitational force on each other. Gravitational force depends on mass and on the center-to-center distance between the objects. All spheres shown in all the diagrams have the same mass and the different radii. Here, all the spheres shown in all the diagrams have the same density and the different radii shown. Think about how mass is affected by density and volume. This is a pretty in-depth problem. I've seen this show up on the AP test once in the past 4 years. What you have to do here is you need to realize that on the formula chart, the equation for density is on there. So in chemistry, you learned that density is a ratio of mass to volume. Mass measured in kilograms, and volume is going to be in meters cubed in most cases in physics. So we start off with that density equation, and then we rearrange it to get it in terms of mass. And I also have an equation for volume. Volume is for a sphere, and it told us that all of these were spheres. This equation for volume is on the formula chart as well. The volume is 4/3 pi r cubed, and then the mass is equivalent to the density times the volume. Well, when I multiply the density times the volume, then I get 4/3 pi r cubed times the density, and that is our mass. So what I did then is I said, well, they want us to rank the gravitational force. So gravitational force is definitely still equal to gmm over r squared. But now I have a new expression for mass, and you can see that this is where it got pretty tedious because I plugged in the expression for mass into both of these variables here, and I did R1 and R2 because that was the radii of the planets, or sorry, the spheres and they were actually touching each other. So the total distance between their centers was the two radii added to each other. And whenever you look at this big equation, and then you look at the different cases up here, the only thing that is changing is the radii, the R values. So I can ignore, not cancel out. So Braxton asked earlier about canceling out all the constants. We're not canceling them out. We're just saying that they will not affect the overall proportionality. They do go into factoring in the overall gravitational force, affecting what this value is, but they don't go into affecting how much larger this one is than this one is when everything else is the same. And so I ignored G, 4/3 pi, and the density of the planets, because those things were all the same in each scenario. The only thing that was different in each scenario were the R values. So really, if you multiply the cubes of the R values and then divide by the square of the sum of the R values, that's what you're going to rank. So the numbers you see that I wrote up here, that is taking the product of the cube of the R's divided by the sum of the R's squared. So let's take this 8/9 for example. We have 2R and we have R. So I'm going to cube that's this R here. Well, and I'm going to cube the 2R here. Well, 2 times 2 times 2. 2 times 2 is 4. 4 times 2 is 8. And of course, this is going to be R cubed, and that's going to be 1R cubed. So it's going to become 8R cubed. Divided by, well, what is their R values added together? We have 2R plus R, that's 3R. If I square 3R, then I have 9R squared on the bottom. In every case, I'm going to have R cubed on the top and R squared on the bottom. So really what I'm looking for is the ratio of the R cubed to the R squareds. And that's how I got the numbers that you see there. And that is how I ranked the gravitational forces. Okay, I hope that helps. Let's go back over. What are your other questions? So I'm back on the chat feature. So tell me, what are your other questions about the practice test or test review? Get this over. It's very loud tonight. I'm so sorry. Hopefully that's all going to change soon. All right, so if there's no specific questions, I'll go ahead and just talk about a few things. You need to be able to identify the types of forces in different circular motion problems. So we did this on a quiz. And the easy part at this point should be identifying the type of force. The more difficult part is going to be drawing the free body diagrams, and then of course ultimately writing those summation equations. So let's talk about turning on a curve. You guys do this every day. Every time you get into your car, you turn. Any trip you're on, you're turning in your car. It does not have to be a complete circle in order to, yes, John, I'll do that next. It doesn't have to be a complete circle to be circular motion. It just has to have a radius of curvature. What is the radius of curvature? Well, this curve, if it were a full circle, would have radius r. So if I'm driving down a road, then the centripetal force that's going to keep me turning is the friction force. And that is going to be equal to mv squared over r. This frictional force also has its own equation. If we remember from our force unit, frictional force is equal to mu Fn. If I have a car here and I were to draw the free body diagram acting on this car, in the vertical direction, I've got the force of gravity and I've got the normal force. If it's just moving in a horizontal curve, like I've shown here, so this is a top view, not a side view. Looking down from the top, if I'm in my car going around a curve, then the gravitational force and the normal force have to be equal. So that is something that I would want to write down if it was an FRQ question. You want the reader to know that you understand that the gravitational force is equal to the normal force. Or the sum of those forces equals 0. So you could also write Fn minus Fg equals 0. Either one of those will suffice. I also know that gravitational force on the surface of the planet is equal to mg. So I'm going to take this expression, say that that is equal to Fn, and that is equal, and friction force is equal to mu Fn. So now I'm going to say that my friction force is equal to mu mg. Because the friction force is the only force creating this centripetal force, it alone is equal to mv squared over r. So now I can take this expression for mu mg, force of friction, and plug it in here. So I get mu mg equals mv squared over r. And now I'm going to simplify. You always want the most simplified version of these equations. This is the mass of the car that's going around the curve. Those masses cancel out. I'm going to rearrange to solve for the velocity. So velocity is going to be equal to, bring the r over, mu g r, and then I'm left with a v squared, so I'm going to take the square root of that. So the square root of mu g r is equal to the velocity. If you know that the coefficient of friction between rubber tires and asphalt is always pretty much the same, you can plug in that value there. That would have to be given to you on a test. You know the g value is approximately 10. Then you can see that the velocity, the maximum velocity allowed around that curve, is really at that point just dependent upon the radius, because we're assuming that most cars have the same coefficient of friction between the tires and the road. So we could say that the velocity is proportional to the square root of r. So if you knew this r value, you could figure out the maximum speed. And that's how the engineers determine the maximum speed needed to go around different curves, and that's why they have certain speed limit signs posted around different curves. Now obviously they're not going to post this maximum speed value because they don't want you going as fast as humanly possible. Because there are also days where it might rain, and or there's oil on the road. And if this mu value goes down, then you can see that that v value is going to go down too. So they're going to post a velocity or a speed that is less than the absolute maximum. Because what you find with this equation is the absolute maximum velocity you can go before you start skidding outwards, before the friction is not enough to hold you in. All right. Nick says, when is there normal force when experiencing weightlessness? There is never a normal force when you experience full weightlessness. So if I feel completely weightless, there is absolutely no normal force. So right now, standing on the earth, you feel a normal force upwards, and of course you've got gravity down. You feel that surface pushing up on you. But if this surface, let's say it was a table you were standing on, and now here's the surface of the earth, this table is now falling with its own weight. You have your own weight. So force of gravity on you, force of gravity on this guy. Both of you are accelerating at 10 meters per second squared. When that's happening, when you're falling at the same rate that this surface underneath you is falling, then there is no longer a normal force pushing up on you. And this is when you feel weightless, when you have absolutely zero normal force pushing up on you. And that's why the astronauts in the space station feel weightless, because the container they're in is free falling, and they are also free falling towards the Earth's surface. Okay, John wants to do 23A. Let's see, is that on the test review or the practice test, John? I guess it'd have to be the practice test, right? (23A). Okay, so we have a Ferris wheel with radius 5 meters. It makes 1 revolution every 8 seconds with uniform rotation. A person who normally weighs 670 newtons is sitting on one of the benches attached at the rim of the wheel. Draw a free-body diagram of the forces on the seated person while moving through the highest point on the ride. Okay, so he said 23A, right? So it's the free body diagram here. So let's think about what a Ferris wheel normally looks like. Ferris wheel, you normally have this hanging cage, if you will, and then you've got a seat over here and a seat over here. You've got some type of hanging basket. But they're wanting you to draw the free body diagram on the seated person. Because they want you to draw the free body diagram on the seated person, I'm now going to look at, well, here's my seat and here's my person. So the forces acting on the person. I'll draw a little dot over here to represent the person. You've got gravitational force of that person, which is equal to the mass of the person times 10. Then you've got a normal force that is going to push up on the person because he is seated, right? So we know we have a normal force. But the question is, how long do I make this vector? Do I make it shorter than the gravitational force, equal to the gravitational force, or less than the gravitational force? My answer to that question lies in this analyzing this bigger picture over here. I can see that there's a radius of curvature up here, and I ask myself, where is the seated person going next? Because he's at the top, right? Where is he going to go next? He's going to go down. He's got to curve down. So where is the radius of the curvature pointing to? Towards the center, it is pointing down. And I know that in order for him to curve downwards, there must be a centripetal force, which is equal to the net force, and it must be in the downward direction. So that means that his normal force is going to be less than his gravitational force. Let me see if I can find my eraser. So we're going to make this less than, and then we go back to the pen, and we're going to say, now this is our normal force. Draw a free body diagram of the forces on the seated person while moving through the highest point of the ride. So we are at the highest point of the ride here. We looked at the macro view, we looked at the micro view, and on the seated person, the ride does not have to push up. The seat does not have to push up on him with his full weight force at the top, because gravity is already going to be pulling him down towards the center of that circle. So, John, did that answer your question? Do you want me to continue with that question, John, or are we good with the free body diagram? Awesome. Okay. Let's see. Reese wants to look at number 15 and number 18. So let's go back to the test. Oops. (15 and 18). 15 and 18. Go back down here. There we go. Okay. A newly discovered planet has a mass that is 4 times the mass of the Earth. The radius of the Earth is RE. The gravitational field strength at the surface of the new planet is equal to that at the surface of the Earth, if the radius of the new planet is equal to blank. So they're basically saying that it has 4 times the mass of the Earth, but that means that its G value would be 4 times that of Earth, because we already saw, let me go back over here, we already saw earlier that gravitational force has 2 equations, mg and big G m1 m2 over r squared. Whoops, square goes on the top. Eraser. Why won't it let me erase? Okay. That's a weird eraser. All right, r squared. So we have 2 equations for gravitational force. If I am not on the surface of a planet, then I would use this one. If I'm on the surface, I can use this one. But if I'm on the surface, I can still use this one. It's just the more complicated one. This is the shortcut. But on the surface of the planet, we could still use the second one, the longer one, because in fact, these 2 equations are equal to each other. So when I set those equations equal to each other, I see that I have 2 masses on the right side, but only 1 mass on the left side. So my question is, which one of these masses am I canceling out? So I will say that this is the mass of the Earth, and then this is the mass of the object. Oops. Object that is on the surface of that planet. This is also the mass of the object that's on the surface of that planet. So that is the mass that's going to cancel out. So then we get a simplification. The gravitational field strength on the surface of any planet is equal to big G times the mass of the planet divided by the radius of the planet squared. So now let's go back to what the question asked. It has, number 15, 4 times the mass of the Earth, and its gravitational field strength is equal to Earth, but they want to know what the radius of that new planet has to be in order for the gravitational field strengths to be the same. So we want this G to remain the same, but we are multiplying this times 4. The mass of that planet is being multiplied by 4 compared to Earth's, right? So if I want the ratio to still be G, what do I need to do to the radius? Well, we see that G is proportional to m over r squared. Again, this big G is the same in both scenarios. You can kind of already see it here. If I want the ratio to remain the same, if I'm multiplying by 4 on the top, then I need to divide by 4 on the bottom. So what do I need the radius to be equal to if I want the radius squared to be equal to 4? Well, you can quickly see, take the square root of both sides, and I want the radius to be equal to 2. So if I double the radius and quadruple the mass, then those 2 effects cancel each other out, because I would have 4 over 2 squared, which is equal to 4 over 4, which is equal to 1. So my G factor, or my G didn't change by anything. It's still G. So doubling the radius, in fact, cancels out a quadrupling of the mass. All right. Reese, did that help you out with number 15? How many people do we have on? It doesn't tell me. Just looking through here. Okay. All right, that was number 15. Let's look at number 18. Let's see. I want to go back here. Number 18. We have a new planet again. We have a newly discovered planet, and it has twice the mass of Earth, but the acceleration due to gravity on the new planet's surface is exactly the same as the acceleration due to gravity on Earth's surface. The radius of the new planet in terms of the radius r of the Earth is. So it's pretty much the exact same question. They're asking me by what factor do I need to change the r value. Let me go back over here. Let's identify again what they said was changing. Twice the mass of Earth, g stays the same. What happens to r? Okay, so if we look at the same derivation we just did, g is equal to big G m over r squared, then we also know that the big G is not changing. This little g is not even changing. That's remaining the same. M and r are what are changing. So to see their relationship to each other, I'm going to move the r to the other side. So I can see r squared, not equal to, sorry, proportional to m. But they wanted to find out what the radius is doing, not the mass. So I always want to get it in terms of, it's kind of like solving for r. You want to get rid of that square root. So I'm going to take the square root of both sides. So r is proportional to the square root of m. What did we do to m? We multiplied it by 2. So if I plug that in, I get square root of 2. This is by what factor I need to change my r. If I look at it in the bigger picture, g is equal to big G m over r squared. If I double mass, remember, this g has to stay the same, this g has to stay the same, and I'm doubling mass. What do I need to do with r if I want this ratio to stay the same? I want this ratio to remain g. Well, I need 2 on top and I need 2 on bottom. R squared has to equal 2. Well, what's the only way that r squared is going to equal 2? If r is the square root of 2, and then when I square it, it's going to be equal to 2. So if you like to think bigger picture, you can play with it this way, or if you do it the way that you get it down to a proportionality in one variable, eliminating the things that do not change, creating your proportionality, then solving for what they're asking you for. Either way works. You can also plug in a value for G, a value for M, a value for R, and your known value for, or sorry, you could plug in a 10 here. You could plug in 6.67 times 10 to the negative 11 here, and you could make up any mass you wanted to here. Solve for R. Then you could go in and double that mass you created. So let's say the mass you created was 1 kilogram. The next time you solve for R, you're going to plug in 2 kilograms. Okay? You can make up whatever mass you want. You just know that it needs to double. And then when you solve for R the first time, and you solve for R the second time, you're going to see how they compare. How much, by what factor, did I multiply R1 by to get R2? That's really what we're doing here. I simplify it by saying, well, this G isn't going to change my answer, so I just ignore it. This G isn't going to change my answer, so I ignore it. And then I find the relationship between M and R. I hope that helps you with your proportionalities. All right, Ethan says, can you do 21 on the practice test? Let's look at it. Okay, 21 on the practice test. What is the magnitude of the gravitational force that 2 small 7-kilogram balls exert on each other when they are 0.35 meters apart? So this is taking 2 small objects on Earth and asking what the gravitational force is between them. You're really just kind of holding them about this far apart. They both weigh 7 kilograms. And we want to know what the force is between them, the gravitational force between these 2 objects. Not between them and Earth, but between each other. Because gravitational force is created by all objects that have mass. So if 2 objects that have mass are near each other, they are going to have a gravitational force on each other. So we have a 7 kilogram ball over here and a 7 kilogram ball over here, and they are 0.35 meters apart. At this very, very, very small distance, we don't really need to know the radius of these balls. We can just assume that that distance between centers is 0.35. So what we're going to get is the force of gravity is going to be equal to, yes, I want the hard eraser. Stop. Okay. The force of gravity is going to be equal to big G, which is 6.7 times 10 to the negative 11, times mass 1, which is 7, mass 2, which is also 7, and 0.35 squared. And then I solve for f of g. If we go back to my key, you can see that f of g comes out to be 2.67 times 10 to the negative 8. Now, if you're not getting the correct exponent, it's probably the way you're entering this problem into your calculator. I use the E button because that stands for exponent. So on the calculator, I would enter in 7.67 E negative 11. This E stands for times 10, and then of course you enter in whatever that exponent is. And in this case, the calculator sees this as a number, one number, just like it would see the number 100. But if you type in 6.67 times 10 to the caret top negative 11, you put in a function here. And your calculator is seeing this as multiplying. So you really have to do order of operations if you use that technique. And a lot of times students do not do that correctly whenever they have a big problem like this. So if it's just a wrong exponent, it's probably the way you're entering the problem into the calculator. Awesome. Okay, Ethan, did that help you with number 21? Or do you have any further questions about that? I hope that was the right one you were talking about. All right, Caitlin says 24A and B. So let's look at that. 24. A small 175 gram ball on the end of a light string is revolving uniformly on a frictionless surface in a horizontal circle of radius 1 meter. The ball makes 2 revolutions every 1 second. All right, here's where we need to just pause for a moment and review what this is really telling us. 2 revolutions every second. So in this unit, we learned that there's a difference between frequency and period. Period is represented with T. This is equal to the time of 1 revolution. And then frequency is F. This is equal to the number of revolutions every 1 second. See how these, ow, down, down, no man. No. Bad dog. Sorry about that. My dog just ate my hamburger off the stove. She's so bad. It's the old one. She's 12. So I feel bad for her, so I try not to get too mad. But when you see her with her paws up on the oven and she's eating my dinner, sorry. Okay. Bad dog. Bad dog. She's in trouble. All right. And okay, so back to frequency versus period. See how these are kind of the opposite of each other? In this one, it's time per revolution. In this one, it's revolution per time. So we can also say the relationship between period and frequency is the inverse, right? So if period is 2 seconds, then the frequency is 1 over 2 seconds to the negative 1, or that is also called hertz. Okay, seconds to the negative 1 has its own unit, and it is called hertz. Now, let's go back to what they told us in the problem. They said that the ball makes 2 revolutions every second. So is that a period or is that a frequency? 2 revolutions every second. Revolutions every second, that is a frequency. So we know that our frequency in this case is equal to 2, therefore our period is going to be equal to a half a second. Okay, let's go back to what the question is asking. Determine the period of the motion. First question is, what is the period of the motion? It's going to be 1/2 based on the explanation that I just gave. B, determine the frequency of the motion in hertz. Again, frequency is just the inverse of period, and in fact, frequency is what they gave me in the problem. So I didn't have to do any work to figure that out. Awesome. Caitlin, did that help you? Lane says, can you do problem number 1 from the review, part C? Let's see. Problem number 1 from the review, part C. Problem number 1, review part C. Rank the moons based on their orbital speed from greatest to least. Orbital speed. Okay, so Lane, what I did here, I'm assuming you understand centripetal force is v squared over r, and then when I rearrange that, the velocity is going to be equal to the square root of the centripetal acceleration times r. These are orbiting bodies, right? So what is that centripetal force that's holding them together? Gravitational force. Remember earlier we said that G is equal to big G M over r squared. This is the gravitational field strength. Gravitational field strength. But it is also the centripetal acceleration in this case. That G is the centripetal acceleration. So what I have done is I've plugged this in for the for the centripetal acceleration. And when I do that, you can see that you end up with one of those r's canceling out. And so whenever I rank them, I'm going to take the square root of gm over r. And of course, the m and the r are the only two things that are changing. So that's how I did that one. All right, what else do we have? Trying to think about everything else we talked about during this unit. For me, I think the most difficult part of this test depends on how good you're at proportionalities, because there will definitely be proportionalities on there. So you need to be able to take that equation, you know, f of g is equal to mv squared over r. If I plug in my 2 pi r there, then this becomes fg equals m. Hello. Uh-oh, what's happening? I'm freezing. There we go. Okay. M times 2 pi r squared over t over r. And then, of course, you can square all this and then simplify. And that's going to come down to 4 pi squared r squared. Why does it keep freezing? Over rt squared, and then one of those r's is going to cancel out. So that squared is going to cancel out that r. So now we have gravitational force in this case would be equal to m4 pi squared. Oh, my computer's hanging up on me, sorry. R over T squared. So now I could ask, if I wanted I already know that all of this is going to remain the same, the 4 pi squared, right? But I could pick 2 of these to remain the same and then say, well, out of the remaining 2, if I change this one, how does the other one change? So if the mass stays the same and the gravitational force stays the same because the mass is the same, what happens to the period as I change the radius? If I increase the radius by a factor of 4, what did the period do? Well, the period is going to have to be doubled because of that squared value on there, because I want it to remain the same ratio. And since I'm multiplying the top by 4, I want to multiply the bottom by 4, but that means the period is only going to double. So being able to do proportionalities like this is going to really help. And then also being able to write your summation equations. So if I have a roller coaster and I'm on the top of the loop, or maybe this is a hill and you're in your car, maybe this is a valley down here. You know that the centripetal force or net force is going to be inward. So in this case over here, your normal force is going to be greater than your gravitational force. So here, normal force would be greater than gravitational force. And my gravitational force doesn't change over here because my mass didn't change, but my normal force is going to be much less because now I need my net force to be down, not up. And I already have gravitational force down, therefore the normal force is going to be much less in that scenario. Then for my summation equation, I would simply say, f of g minus fn is equal to mv squared over r. All right, it looks like my battery is running pretty low. I do need to go help get the kids in bed upstairs. So I'm going to have to, let's see, I have one more problem. Can you tell me? Sorry, this is not related to the webinar, but for the book work that is due, do you want us to complete all the problems or just the questions you assigned? I would say, did I not assign all the problems that are in the packet, in the back of the packet? I'm going to pick up those last 2 pages of the packet. Interesting. Well, then I would just say do the ones that I assigned, unless you want to do the others for practice because you think it'll help you on the test. But I'll only grade the ones that I assigned. Awesome. Thank you guys so much for joining me tonight. I was happy to do this live webinar for you. And I will be there before school tomorrow morning. So if you have any other questions, you can stop by to see me. I'm going to get this recording stopped